Great, so let us start. Last time we essentially closed a chapter where we discussed what is the organization needed to get self-referencing programs, but it's a priori not clear how will that lead to a design of a physical self-replicator, so a machine that can really manipulate the parts around itself and build an exact copy of itself. And that's why today we will present the solution to this problem by John von Neumann. So you can keep the Kleen's recursion theorems in the back of your mind during these two lectures. But you can really see von Neumann's result as independent of those, even though we will discuss some connections at the end of this chapter. So let us start this new chapter. So I was surprised in the initial lecture that essentially most of you have not heard about John von Neumann, even though he really contributed to an astonishingly wide range of fields. So I managed to find a documentary from 1966 about him that could be interesting to watch. And for us, we can now watch a snippet of it, which is about Edward Teller recounting, narrating his views on John von Neumann. So yeah, as was mentioned by Edward Teller, that was a real Edward Teller, by the way, John von Neumann was interested in a lot of things, and in the late 1940s he was interested in the connection between neural system and computing systems, and he drew some interesting parallels between the two. And yes, one particular question he was posing to himself was, what is the necessary or sufficient logical organization such that a computing system or a machine could self-replicate? And he came with two original ideas at the time. So the first idea was to split the machine into two parts. This is something we discussed already, but the idea is due to John von Neumann. So one part is the tape, which contains the information or instructions for the machine. And the other part is the functional part of the machine, we can call it, the machine, which processes this information and according to it can manipulate parts around itself and maybe build other machines. And the second original idea was that in order for this self-replicating cycle to be fully complete, we have to use the information on the tape twice. Once to be interpreted so that the new machine can be built according to the instructions, and once to be transcribed and copied onto the empty tape of the new machine. Only then can the new machine start self-replicating. And this particular organization predicted the essence of biological self-replication before the discovery of DNA. So he gave a series of talks where he discussed these ideas at the University of Illinois in 1949. And the paper which discussed the structure of DNA was in 1953. So let us look into the detailed argumentation of John von Neumann. Essentially, when he first started thinking about this topic, he already accounted for or worked with a very abstracted model of the physical world that we will call the kinematic model. As we will see, it still would be extremely tedious to work out the proof into all the formal details, but we will use this model to respect the historical, let's say, sequence of events and explain the core ideas behind John von Neumann's work on self-replication on that model. And then we will move to the tedious work where we really formalize and construct the self-replicator in an even more abstract model based on a cellular automaton. So this will basically take us this week and next week. So let's start with the kinematic model. So this model we can imagine to be a three-dimensional space. With some free-floating elementary particles. So let me specify what are the types of particles that he considered. Not that it would be crucial, but just to make the argument as concrete as possible without going into too many technical details. So there were two types of particles. One that we can call, let's say, the informational layer or information processing. Which consists of some particle that can transmit signals, so some signal transmission particle. Then some pulsar, which generates signals. And then particles that implement some basic logic gates. So let's say and, or, and not. Essentially, that's all we need to build an arbitrary Boolean circuit. And the second type of particle he considered would represent the actual matter, let's say the physical matter. And the baseline for that is the rigid particle, through which signals cannot pass, and it's really just a sturdy piece of matter. Then some, it's probably not called like this, but the gluing particle, which can essentially connect two rigid elements together, and then some cutting. Which can just separate these two glued rigid elements again. Also the so-called muscle particle, which can essentially contract and relax and be attached to other rigid elements, and as such it can somehow, it enables movement in this world. And this is where we will not go into the technical details, and we will make a huge assumptions, is that we can assume that these particles are rich enough that we can build from them any functional unit that we can think of. For instance, we can build from it a sensing unit, which would be some kind of arrangements of these elements, that when it comes into contact with a free-floating particle, it will be able to tell what type of particle it is. Another kind of higher level building block would be some construction arm that can actually build that element and manipulate it and connect it to other elements. And for instance, one such higher level organization would be a one-dimensional tape, which we can kind of imagine as being made of the rigid elements. So each of this is a rigid particle. Each of this is a particular connection. And this tape can encode binary information. Like every rigid element that has only two neighbors represents 0, and every one that has 3 neighbors represents 1. Is it clear? And the biggest assumption that we will make is that from these elements, we can also build a Turing machine that operates on a tape made from the rigid elements. It will be tedious, it's probably would be possible, but this is really the crucial observation John von Neumann made, is that if we want a machine to self-reproduce, then the notion of Turing machine is not a suitable one for the following reason. So a Turing machine's output is a sequence of symbols on a tape, and that is not another Turing machine. So the space of its outputs is different from the objects themselves, so it is just not possible in the clear terms of self-replication for a Turing machine to produce another Turing machine. As we have discussed last time, essentially a Turing machine can produce its own description, but that description is a different object from the Turing machine themselves, like the Turing machine itself. The description cannot start operating on its own tape. It does not have a tape, right? So the crucial observation is that we have to consider some embodied version of a Turing machine. That is, we have to identify some basic elementary building blocks, like the particles in the kinematic model, out of which we can build both the Turing machine and its tape, such that the outputs of the Turing machine live in the same space as the Turing machine itself. That is just an ensemble of some elementary particles. So crucial observation is that we have to consider an embodied version of a Turing machine in order for it to be able to self-replicate. So we assume that we can really build some structure in this space made from some elementary particles, which has some construction arm, which has its tape. And analogously to the idea of Turing, which is something von Neumann acknowledges, we can assign to every such pattern its description. And we can assume this description to be binary. So if this is some machine M, then we can assign to it some description M, which is just a binary sequence. And this means we can represent this sequence by the tape. So we make a crucial assumption that we can build a universal constructor out of the elementary particles. So again, this is an idea that is quite analogous to a universal Turing machine. But what we mean by a universal constructor is such an organization of the elementary building blocks such that if we have some machine X and we put on its tape the description of X, then M will be able to interpret this and kind of find the elements in this space. We assume that all of them are in abundance so that we don't run into resources issues, but it will be just able to connect them and organize them in such a way to actually construct X. Like the description, it's not so hard to imagine that it literally says find element A, connect it to element B, then connect it to element C, and so on. We will call this B. So B is such a machine that is a universal constructor. And we will make a second assumption, which is the existence of yet another machine. We assume, oh, this chalk is painful. The existence of a copy machine A, which can produce an exact copy of its tape. So it is not so difficult to imagine how A would look like. It would just read every bit on its tape sequentially. Yes?
Here, when we talk about machines, we always talk about like the physical implementation of the conceptual idea of a Turing machine in this world of particles.
Yeah, essentially. Essentially, we talk about an ensemble of elementary particles that has to it attached some tape. And as it starts operating, like it will have some signals going through it, and it will be doing something to the tape, and it will be doing something to its surrounding world. So in some sense, it's a bit more than a Turing machine because it not only manipulates the tape, it can also manipulate the elementary particles around it. So it's like a, really like a constructing machine of some sort. But yeah, this all is a bit informal. So why is this not so far-fetched to imagine the existence of this machine? Is precisely because this tape is one-dimensional and can be read sequentially. Like it would be a bit trickier to design such a machine if the tape was a three-dimensional cube. Like how do we access all the information without destroying such an object? But this should be fine. And now we can design we define a machine R which upon receiving the description of a machine X, it acts as follows. So first, so we can imagine R to consist of two parts, of the machine B and of the machine A. So first it triggers the function of B, which builds X without the tape. This is the translation process. And then it activates A, which copies the tape of R and attaches it to the newly built machine X. And now it's, so in some sense, R is the composition of first B and then A. Yes? So we started by discussing that each machine is decomposed into, or like each entity in this space is decomposed into two parts, some processing unit and the tape.
So all machines by default have a tape?
Yes. So what B does, it builds this. It builds whatever is, so yeah. What B does is kind of, it builds the processing part. What A does, it copies the tape. And now we should not be surprised what happens when R receives its own description R on the tape. Yeah, so first B builds R and then A copies the content of this tape. So we have somehow R, we have the tape that contains R, and after some time steps in this world, there will be the original machine, and there will be an exact copy of it. Mm.
So the machine B doesn't touch the description?
No. It just reads it instruction by instruction and manipulates the particles it sees around itself. So here we can notice some loose parallel with our Quine construction. Inherently, every self-replication process is deeply self-referential. So there must always be a mechanism which overcomes the seeming paradox of this self-reference. And in the Quine construction, we did this by decomposing the Quine into two parts, A and B. B had some functional role, like a pretty rich functional role, and what it did is that whatever it saw on the tape, it found a description of a machine that prints that, and it added that to the tape and combined it with what is on the tape to kind of get a description of a machine that is the composition. Yeah. And A had some data role. All it had to do was print the description of B. This was hard-coded into A. And we can notice some kind of analog, but I don't want to go too much into it here. We're also overcoming the seeming paradox of self-reference by decomposing this machine R into two parts. B is this universal constructor. No matter what it receives on the tape, it will just build it if it was a valid description of some pattern. And A has the data role. It just copies the data. So one more interesting remark is the seeming paradox of self-replication that we discussed at the beginning of the course, which is that if a machine A was to build a machine B, then intuitively it seems that A has to have complete information about B, somehow hard-coded within itself, and on top of it, it has to contain the mechanisms that can act upon this description so that it can build an actual machine. So it somehow seems, for an unspecified notion of complexity, that A has to be strictly more complex than B. So how is it possible that one machine can build another machine of the exact same complexity? And this paradox is explicitly discussed by John von Neumann, and he has a very interesting explanation of it. So he suggests that we assign to each machine some notion of complexity. Intuitively, this notion of complexity should describe the rich functionality of the machine, but that's by far a formal definition. To this day, we do not have one. But very roughly, if we live in this embodied space where everything is built from some elementary building blocks, we can approximate the complexity very roughly just by measuring the machine's size. And he says, well, if the machine's complexity is below a certain threshold, it will only be able to construct machines simpler than itself. And if we look at the lineage of such machines, its complexity will be degenerative. And this is why we have this intuition, is that most machines we see, like a bus or some construction arm building some car parts, is not complex enough, or like is exactly below this complexity threshold, and that's why it only builds entities that are less complex than itself. But he says, if we did overcome the complexity threshold, for instance, by creating a machine that is a universal constructor, then suddenly the machine can build machines of exact same complexity or of itself, or even larger, because now this machine does not have any descriptions hard-coded into itself. It is just rich enough in functionality that it can interpret whatever it receives as instructions on its tape, so the complexity can be offloaded into the content of the tape. If the universal constructor R received on its tape a description of a machine that is much bigger or more complex than R, it would still build it. And the description would probably be long, but it does not matter to R. So he essentially says that above a certain complexity threshold, if we looked at the lineage of machines that one built another one and so on, actually the complexity can be expansive. So I thought this was an interesting idea to share. Yeah. And it actually points to the core of the artificial life, because we are now talking about exact self-replication. How is it possible for a machine to build exact copy of itself? But this idea of von Neumann is actually aiming towards a much grander goal. That is a machine that can build a machine that is more complicated than itself. So already pointing towards some evolutionary process. But we will only discuss this later. Let's now go back to the exact self-replication. So yeah, judging by your questions, it's pretty clear that this was, hopefully it was clear, but it was still an informal illustration of von Neumann's idea. And to make it precise, we would have to deal with a myriad of technical details. So how do we exactly deal with movement in this continuous space of these discrete particles, and so on. And that really distracts us from the main goal, which is to understand the logic of self-replication. And this is why, after von Neumann discussed with Ulam, who suggested him to try a different model, which is much more amenable to a formal mathematical approach, the cellular automaton, von Neumann did switch to it and essentially almost completed this construction. Unfortunately, he did not finish the manuscripts before his death, so they were posthumously collected by Arthur Burks and published, but yeah. It was clear that his ideas went far beyond what he managed to publish. So, great. Let me show you another video. This time it will be a discussion with another Nobel laureate, Sidney Brenner, about the connections between von Neumann's work and molecular biology. It's really interesting.